Bonjour. Here we are, our first section in Unit 6. Wow. It's, depending on what day you have me, it's February, right? So we're starting Unit 6, and our first section, our first lesson is about our nth roots and rational exponents. So basically, we're simplifying exponential and radical expressions, okay? So a lot of this is going to be a review, but we're going to be bumping it up a couple notches. So the first thing that's really important are the powers that you need to know without a calculator, recognizing them by taking the cubic root or the square root or the fourth root, or cubing them, squaring them, whatever. So just giving you a list as an example, like you should know that 2 squared is 4. You should know that 2 cubed is 8. You should know that 2 to the 4th would then be 16, and 2 to the 5th would then be 32, and 2 to the 6th is then 64. And I mean, 2 raised to any power should be pretty easy, but those are ones that you should kind of be able to do in a matter of a second. And then 3 squared, obviously 9. 3 cubed, 27. And then 3 to the 4th would be 81. 4 squared, obviously 16. 4 cubed, 64. 4 to the 4th would then be, caught me off guard there. I don't know which one that is off the top of my head. 4 times 4 times 4 times 4 times, 256. Duh. Miss Trees, I should have known that, because 4 to the 4th is the same thing as 16 squared, because I know that 4 squared is 16. Remember, when we raise a power to a power, we multiply those powers. So 4 to the 4th is the same thing as 4 squared, and I know that 4 squared is 16, and I know 16 squared is 256. And then 5 squared, obviously 25, 5 cubed, 125, and then 5 to the 4th, if we use that same process, that it's 5 squared, 25 times 25 would give you that 625. And then, of course, really 6 squared, 7 squared, 8 squared, 9 squared, all the way through 15 squared. You should know those by the drop of a hat. And then 10 raised to any power, you should know, because it has that total amount of zeros. So, like I said, we need to get into this review of just simplifying these radicals. Most of them are square roots, but we might get into cubic root or the fourth root, or simplifying things with exponents, fractional exponents, negative exponents, etc. So, first one is the square root of 32. So remember, when we're just taking the square root of a number, we can factor that number if it's not a perfect square, which 32 is not. So technically, I'm looking for factors of 32. So you could go small and go like 2 and 16, or you could, go bigger than that if you want it, whatever. I'm going to go 2 and 16. And a trick here would say, well, I know the square root of 16 is 4. So then this would just be 4 radical 2. But if you can't see that, then you would continue to break it down. Maybe you see the 2 and the 8. Maybe then you go 2 and 4. Then maybe you go 2 and 2. At this point, when you reach prime factorization, you're looking at all these numbers, and because it's a square root, so I'm basically asking myself what times itself gave me that number. I'm going to look for 2 of a kind. If this was a cubed root, I would look for 3 of a kind, because I'm asking myself what times what gave me that number. So looking at 2 of a kind, this would give me a 2, this would give me another 2, and then I have that left over. Everything gets multiplied. I get that same for radical 2. We have done this before this year. I know you did a lot of this in geometry as well. When we're raising something to that negative power, remember that means that it's going to drop down into the denominator. So we almost create a fraction and drop it in the denominator. If we already have a fraction, it just changes locations. If the negative exponent is in the denominator, it shoots up to the numerator, vice versa. So really, if you need to rewrite this as 1 over 4 to the second power, then obviously that's just going to be 1 over 16, which cannot be reduced. A fractional exponent, that is when we have a fractional exponent, the denominator of that fraction, so in this case 2, is the root. So the root is on the bottom. That's kind of what it's saying right here. So the root that I'm taking is the second root, or the square root of 4 to that first power. So we're technically rewriting this as the squared root of 4 to that first power, which we just know is the square root of 4, which we know is 2. Okay, we need to be really, really careful when it comes to D and E. There is a huge difference here. In D, if we follow order of operations, we are squaring the 7 and then multiplying the negative to that, which would make it a negative 49. In E, we are squaring that entire thing in the parentheses, which is the negative 7. When I square a negative 7, I always am going to get that positive 49. So if you are squaring a number and you see a negative and it's not in the parentheses, then your answer is going to be negative. If you are squaring a negative number and it is inside the parentheses, then you will obviously always get that positive. Okay, so we had the 2 here, and the 1 over 16, and the 4. Okay. In F, we are multiplying some variables together with exponents. So anytime we have the same variable and they're being multiplied, we are going to add the exponents. So this means I'm going to have x to the 6th power and y to the 8th power. In G, we're raising powers to powers. So I'm taking that x squared and squaring it. I'm taking that y cubed and squaring it. So I'm squaring a square and squaring a cube. When I raise a power to a power, I multiply the powers. So this is going to be x to the 4th because 2 times 2 is 4, and y to the 6th because 3 times 2 is 6. When dividing things with exponents, we are going to subtract those exponents. But remember, we can only do it with like terms. So the x's stay with the x's and the y stays with the y's. So if I have x to the 7th divided by x to the 4th, technically that would be an x to the 3rd power. I have a y to the 3rd divided by a y to the 8th. So technically that is a y to the negative 5th power. 3 minus 8. I have to go in that order. I'm not dividing y to the 8th by y cubed. I'm dividing y cubed by y to the 8th. So I have to make sure I'm going in the correct order of subtraction. And I'm not going to leave my answer like this. I am going to utilize that property of a negative exponent, and that means it's going to drop down into my denominator. So I have x cubed now divided by y to the 5th. Okay, another power to a power, but this time we do have a fraction. Anytime you're raising a fraction to a power, you actually apply that power to the numerator and the denominator. So this is actually x squared raised to the 3rd power, and then y raised to the 3rd power. So raising a power to a power, we multiply, and then just y to the 3rd power. They are not the same variables, so we cannot subtract those exponents. That is our final answer. In J, notice that exponent is pretty much the same exact question as I, but notice that 3 now is negative. So technically, we're doing 1 over this fraction, right? But another way of writing that is just reciprocating that fraction. So it's really just y over x squared, but still raised to that 3rd power. So it would actually be y to the 3rd over x to the 6th. So the same exact answer, just flipped because that 3 was negative. In K, we because we're adding, we can only add or subtract like terms. And what makes a like term is that the number underneath the radical has to be the same. So 2 radical 3 and 5 radical 3 are like terms. That's like saying 2x plus 5x, which we can do, and that's 7x. So this is going to be 7 radical 3. We do not add what's underneath those radicals. That's for adding and subtracting. They have to be like. So I could not have done something like 2 radical 3 plus 5 radical 2. That would not get me 7 radical whatever. This would be my final answer because those radicals are not the same. If I'm multiplying or dividing, then of course I can combine those. And when I multiply for like L, I actually multiply the constant or the whole number with the whole number, and I multiply the radical with a radical. So this would then be 2 times 5 is 10. Radical 3 times radical 2 is radical 6. Final answer. And then I have 1 over radical 2. We never want to leave a square root or a cubed root or any kind of radical in our denominator, because remember, a radical is an irrational number, which means it's a number that doesn't repeat or end. So there's no way that we could make a fraction of that. Think of fraction as like a pizza slice or a cake slice, right? I can't cut up a cake into the square root of 2 pieces. It's literally impossible. So to rationalize this, we start with our problem. Our problem is the square root of 2 in the denominator. So I multiply by 1, but I make 1 special. You can write the number 1 infinite amount of ways. You can write it as 5 over 5. You can write it as 1. You can write it as square root of 2 over square root of 2. That version of 1 is going to get us rid of that radical in the denominator, because I multiply top to top, bottom to bottom, and now we do not have a radical in our denominator anymore. I'm going somewhat fast through these things because you should already know these properties. And if you don't, then you need to go back and work 6.0 or do some Googling or come to tutorials or something. This is the easy part. Everything we do after this is applying these properties like that, okay? So now's your chance. If you need help, stop the video, go do 6.0, Google, talk to me, whatever. Okay, so example 1, we want to rewrite our radical expressions. We need to rewrite these fractional exponents as a radical expression. So remember, we said that a fractional exponent, the root is always on the bottom. So if I'm dividing by 2, I'm taking the square root. If I'm dividing by 3, I'm taking the cubed root. And if I'm dividing by 8, I'm taking the 8th root. So the root is on the bottom, just like a tree. We cannot take the odd root of, you can take an odd root of a negative. Think about that. When I have negative 2 raised to the third power is an odd degree, or whatever, I get a negative result, which means I can take the cubic root of a negative 8, because I know negative 2 times negative 2 times negative 2 gave me a negative 8. There's no way that I can take an even root of a negative number, because anytime I square a negative, I get a positive, or if I square a positive, I get a positive. So there's no way that I multiplied something to itself and got a negative number. Therefore, I can't take the square root of a negative, which is why we had those imaginary numbers. But that's true for all even roots, not just 2. 4th root, 6th root, 8th root, etc. And that's that last statement there. So here we go. Rewriting as radical expression. So remember, the root is on the bottom. So this means I'm taking the 4th root of x cubed. This means I'm taking the 9th root of y to the 7th. That's all we want to do right now. We're just rewriting. We're not simplifying. We're not doing anything. We're just rewriting it. Okay, for C and D, you have to notice the difference. There's a lot of differences, but one really, really, really important difference is that there are no parentheses in C and there are parentheses in D. What does that matter? Well, in C, that exponent of negative 1/4 is only being applied to the y. The x has a power of 1 there. The x, nothing is happening to the x. The y is what's being raised to a negative 1/4 power. In D, because x and y are both inside those parentheses, that means x is being raised to that 1/2 power and y is being raised to that 1/2 power. Okay, huge, huge difference here. So in C, if I'm just focusing on that y, because it's negative, I know it's going to go in my denominator. So I already know I have a fraction. X is actually chilling at the top. We don't do anything with it. There's no root, there's no nothing. Y, we said, was going to be in the denominator, so that takes care of the negative. It's going to be the 4th root of y to the 1st power. You do not have to put that 1st power there, and I would actually advise that you don't, please. Okay, so that's it. In D, remember I said we're raising both the x and the y to that 1/2 power, which means we're taking the square root or the second root of both that x and y. Both of them are raised to that 1st power, so again, we do not have to write it. If you want to do this, that's technically fine, but really me seeing this extend over both the x and y is what I want to see. I do not want to see something that looks like this. Square root, hold on, let me try that again. Square root xy. That, I would not take the argument that you would try to say of, oh, I meant to put it over both of them. No, this is something completely different. I need to see it physically completely over both, or I need to see those parentheses. I don't really want to see the parentheses. I really want to see your radical extend over. For square root, if you put the two, great. If not, you know that it's understood. Just the root is always a square root. If it's anything higher than that, you need to put, we call that the index, okay? You need to put the 3, the 4, the 9, the whatever. But if it's 2, you can put it or you could not put it. All right, so now we're doing the opposite. We're taking those radical expressions and rewriting them into rational exponents. So remember, look at our differences in parentheses and not parentheses. And how the square root extends, or the fifth root, or the third root, or the eighth root, or whatever, how it extends over the whole thing. So remember, the root always goes in the denominator. The root is at the bottom. So for A, I know both x and y, let me change my color, both x and y are being raised to the 4/3 power. Both x and y are being raised to that 4/3 power. In B, notice that the xy is not in parentheses. So this means that the x has an exponent of 1 underneath the radical, and the y has an exponent of 4 underneath that radical. So technically, if I were to separate these, that would be x to the 1/8 and y to the 4/8. But I can simplify that because I know that 4/8 is just 1/2. So again, notice the difference between A and B. In A, they were in parentheses, meaning that x got that exponent of 4 and the y got the exponent of 4. In B, it wasn't. X only gets that exponent of 1 and y was getting the exponent of 4. Okay. And then we have C. So the whole entire thing is being raised to the 6th power. And then what's inside the parentheses is a cubic root of -5. So I really want to take this step by step. So the first thing I want to do is work what's inside the parentheses. So inside the parentheses, I have a -5 raised to the 1/3 power. But then all of that inside the parentheses is being raised to the 6th power. Well, when I raise a power to a power, I multiply. 1/3 times 6 is actually 2. So that -5 is actually being raised to the 2nd power. And I can simplify that because I know a -5 squared is a positive 25. Okay. So I know it looked a little bit overwhelming at first, but just take it step by step. Work in and your way out. Same thing for D. Notice that we have a fraction underneath the radical. That means that radical, this 5th root, is technically being applied to the numerator and the denominator. So if you want to split that up to help you, this would look like the 5th root of x to the 10th power divided by the 5th root of y. So that might help you because now you can say, well, this is x to the 10/5 over y to the 1/5. And then I would simplify just one more time and say that this is x squared over y to the 1/5. Technically, you should know that y to the 1/5 is a radical in your denominator, so we would have to rationalize. But for the sake of this problem, we just are wanting you to rewrite, so we're not going to make you rationalize for that particular problem. But if the problem just said simplify, then yes, we would expect that you would rationalize your fraction. So then notice example 3 says simplify without a calculator. Here's where those top numbers that you should know really come in handy. You should be able to recognize, oh, 27 is a perfect cube. I know the cube root of 27 is 2. Or I know, that the square root of 16 is 4. Or I know, you should be able to kind of rattle off these numbers off the top of your head. The first thing we need to do, though, is that we would probably want to rewrite some of these, because for me personally, it's harder to simplify when you have a fraction exponent rather than simplifying when you have a radical expression. So I'm going to rewrite these as radical expressions, and then it'll be a little bit easier for us to simplify. So the first one, we have 27 raised to the 4th third. So remember, this is going to be the third root of 27 to the 4th. We now want to simplify this. Let's think about working smarter, not harder, okay? Technically, could we do 27 to the 4th power and then take the cubic root of that big number? Sure, but do you know off the top of your head without a calculator what 27 raised to the 4th power is? No, neither do I, nor do I want to, because that's a very, very large number. But I know that I read left to right, I graph left to right, so I'm going to evaluate this left to right. What is the cubic root of 27? 2. What is 2 to the 4th power? 16. Boom, baby. Done. Yes, it is that easy. And how cool is that, right? Work smarter, not harder. Let's try it again. In B, we have 16 raised to the 5/4. That means I'm taking the 4th root of 16 to the 5th power. I don't know what 16 to the 5th power is, but I know that the 4th root of 16 is 2. So now this is 2 to the 5th power, which makes my life a lot easier because I know 2 to the 5th power is 32. 4 to the 1/2. That means I'm taking the square root of 4. 2. Okay, that's it. Done. Notice I didn't have plus or minus 2 here. Reason being is because I'm not solving for something. If I had x squared equals 4, then I would be taking the square root of 4 and I would want x is plus or minus 2. Because I know this degree is 2, I should have 2 zeros, right? I should have 2 roots. I'm not solving anything here, I'm simplifying. There's a difference. So when you're simplifying the square root of 9, the square root of 4, the square root of 25, we just want those numbers, right? It's 5, it's 2, it's whatever. If you are solving, then that's when you need to include the plus and the minus, okay? 4 to the negative 2nd power. Remember, that's really the same thing as 1 over 4 squared, which is going to be 1 over 16. Final answer. And then e to the negative 1/2 power, so kind of combining c and d together. So that would be the same thing as 1 over the square root of 4, which would just be 1/2. Okay. F, 9 raised to the negative 3/2 power. So again, because it's negative, I want it to go in my denominator. So really, even if you had to rewrite it like this first, and then rewrite it as the square root of 9 cubed, you can totally do that. Whatever you need to do to make you feel successful. Remember, I don't want to sit here and do 9 cubed and then take the square root of it, but I can take the square root of 9 and then cube it. Well, the square root of 9 is 3, and 3 cubed is 27, so this is 1 over 27. Okay, look at G, H, and I. All of them are very, very similar, but very, very different, okay? Main difference in G and H, because the exponent is the same, they both have a negative. One is inside the parentheses, one is not. So in G, how we would write this is that we are taking the negative 6th root of, what is that, 1 million? Yes, 1 million. So how many zeros are there? 6. So what is the 6th root of something that has 6 zeros? Not 1, but 10. And because there's a negative in front, our answer is negative 10. Okay. H was different. The negative was on the inside of parentheses. So that means we're taking the 6th root of negative 1 million. Again, 6 zeros, 6th root. should be 10. However, this is an even root. Can I take the even root of a negative number? No. 10 to the 6th power is a positive 1 million. There's no way that I could raise 10 to the 6th power and get a negative 1 million. So what does that mean? Well, this means no real solutions. It would be some kind of imaginary number that we don't even know about, because the only imaginary numbers we know are the square roots of negative. We don't know anything about the 6th roots. Okay. All we need to know is that I can't take the even root of a negative. No real solution. But we can take the odd root of a negative, right? So that's exactly what we're going to do in I, because that negative is inside the radical. This time we're taking the 5th root of negative 100,000, right? Oh, did I put an extra zero? No. 5 zeros, 5th root, it's going to be 10, but this time it's going to be negative 10, because we can take the odd root of a negative. Negative 10 raised to the 5th power does give me that negative 100,000. Okay. Sweet. Okay, getting more complex here. Use the properties of exponents to simplify. Assume all variables are positive. Rationalize if needed. So notice it says it this time. We are simplifying. We're not simply rewriting. So we do need to rationalize if needed. So here we go. A, 3x to the negative 1 power over x to the 3/5 power. In the numerator, what is being raised to the negative 1 power? Is it the 3? Is it the x? Is it both? Is it neither? It's only the x. 3x is not in parentheses. Therefore, x to the negative 1 power is the only thing, right? The 3 is normal. Well, if the x is raised to a negative power, it goes in the denominator. So that means I have 3 in my numerator, x to the 1st power down here, and I still have the x to the 3/5. Okay. Well, I know that when I multiply things with exponents, I add the exponents. Well, what is 1 plus 3 over 5? Well, if you need to rewrite 1 as 5 over 5 and then add, you would get 8 over 5, x to the 8 over 5. Fine and dandy. However, that's technically a root. That's technically a radical in your denominator. Therefore, we need to rationalize. Earlier, when we rationalized, we just were dealing with a square root. And so we just said, well, let's multiply by that square root over itself. Well, that's not always how we rationalize. Here's why. If I were to just multiply by x to the 8 over 5 over x to the 8 over 5, my denominator would then become x to the 16 over 5, which is still a radical. I'm trying to get a whole number exponent. Fractional exponents are radicals. Whole number exponents are not. I'm trying to get to a whole number exponent. And if I know that I'm going to be adding these exponents, what do I need to add to an 8 over 5 to get a whole number? 2 over 5, because 8 over 5 plus 2 over 5 is 10 over 5, and 10 over 5 is just 2. I can have x to the 2nd power in my denominator. That's totally fine, right? So that's what I'm going to do. X to the 2/5, x to the 2/5. My numerator, 3x to the 2/5 over x to the 10/5. Let's rewrite that as 3x to the 2/5 over x squared. Nothing wrong with that. Okay. Also, if you do want to rewrite this as 3 times the 5th root of x cubed over x squared, that's fine too. I'm not going to be picky about that, whatever you prefer. I'm kind of writing big. I might get in trouble here. Okay. I'll just do that. All right. Let's try it again. we got a lot of parentheses here. 27 over 8 raised to the 1/4 raised to the negative 4/3. Well, let's do something first. Let's do the power to the power. When I have a power to a power, I multiply the powers. What is 1/4 times negative 4 cubed? Negative 4/3. That would be 27 over 8 raised to the negative 4 over 12. Well, I can simplify 4 over 12. 4 over 12 is just 1/3. So really I have 27 over 8 raised to the negative 1/3 power. This is much more manageable to me. 27 over 8 raised to a negative 1/3 means I'm going to reciprocate that fraction. Remember, whatever's in the numerator goes to the denominator. Whatever's in the denominator goes to the numerator when we have a negative exponent. So technically I now have 8 over 27 raised to just a positive 1/3. Well, let's rewrite that as a radical expression. That's the cubic root of 8 over 27. And lucky for us, I know the cubic root of 8 is 2, and the cubic root of 27 is 3. So my answer is 2/3. All right, and last one. Looks overwhelming, but we'll be fine. Combine everything we can and then simplify. Well, because I have two x's in the numerator, that means I can multiply those together. When I multiply those together, I need to add my exponents. That means I'm adding a 2/3 with a 5 over 9. You might want to rewrite this as 6 over 9. That way you're getting 11 over 9. So this means I have x to the 11 over 9 times the y to the 1/5, still divided by the y to the 1/3. Well, now I look at my two y's. What can I do with those y's? Well, I can combine them. When I divide things with exponents, I subtract the exponent. So now I'm doing a 1/5 minus a 1/3. When I'm adding or subtracting fractions, I want that common denominator. Common denominator here is 15. That's 5 over 15. That's 3 over 15. So what's 3 over 15 minus 5 over 15? A negative 2 over 15. So technically, this now becomes x to the 11 over 9 and y to the negative 2 over 15. But we know what to do when we have a negative exponent. We bring it to the bottom. So now we have x to the 11 over 9 divided by y to the 2 over 15. I can't leave my answer like this because I have a radical in the denominator. That's technically the 15th root of y squared. So I need to multiply by something that is going to make this, that's going to add to that exponent to make a whole number. So what plus 2 over 15 will give me a whole number? 13 over 15. If you want to call that like the complement or the remainder or whatever, it's like how many more slices do I need to make that whole pizza, or how many, like whatever. You want to fill in that whole. You want to make a whole number. And so you always multiply with that to the top and the bottom, because this is now just one and I'm not changing my problem any. So now, of course, I have that x to the 11 over 9 times y to the 13 over 15 over just y to the 1 power. And I don't have to put that. And it's fine to have a variable in my denominator. It's not fine to have a radical in my denominator. I know it looks ugly, but that is totally fine. That's your answer. Okay, so some more properties of radicals. Remember when we kind of already worked these out. The product property and the quotient property. So if I take any root of two things being multiplied, I'm taking the root of one and the root of the other. Same thing with the division problem. If I'm taking that root of a fraction, I'm taking the root of the top and the root of the bottom, which is very, very helpful for us. We're going to be simplifying a lot, right? Well, a radical is in simplest form when no radicands have perfect nth powers as factors other than 1. No radicands contain fractions, and no radicals appear in the denominator of a fraction. So the radicals appearing in the denominator is what we've been working with. Radicand is what's underneath the radical. So basically, you just want to make sure that everything is simplified as much as possible. And we don't want to leave a fraction in underneath the radical. So let's simplify. And really that's the rest of our notes is just simplify, simplify, simplify. Okay. So we have, let's go to that hot pink. 2 to the third root of 6 times 5 to the third root of 12. When multiplying, we can multiply these together even though what's underneath the radical is not the same because the radical itself is the same. I can multiply a cubed root of something times a cubed root of something else. So multiplying, I take whole number times whole number, so 2 times 5. Always is still the cube root. It's always the same root. 6 times 12 is 72. This is not my final answer because 72 can be simplified. So remember, this time I want the cubic root of 72. So when I go and I find factors of 72, I'm actually going to be looking for 2 of a kind, I'm going to be looking for 3 of a kind, not 2 of a kind. So you can factor 72 by 36 and 2, or you can go 9 and 8, or whatever. So let's say we go 9, we go 8, and this is really the cubic root. And then we break it down and we get, I'm just going to work with the numbers if that's okay with you guys, because technically that's cubic root. So then let's go 3 and 3, let's go 2 and 4, then let's go 2 and 2. So the numbers we're working with are technically the cubic root of 3, the cubic root of 3, the cubic root of 2, the cubic root of 2, and the cubic root of 2. I need 3 of a kind because I'm working with cubic roots. Boom. That means I have a 2 times a cubic root of 3 times a cubic root of 3, which is 2 cubic root of 9. So I have 10 times 2 cubic root of 9, which means I have 20 cubic root of 9. Okay, let's try it again. 4th root of 80 divided by the 4th root of 5. You could simplify the 4th root of 80 all you want and then do some division, but how about we just divide 80 by 5 because they're both 4th roots. Make your life easy. Work smarter, not harder. The 4th root of 80 divided by the 4th root of 5 is the 4th root of 16. And if you're smart, which I know you are, you should know what raised to the 4th power gives me 16. 2. Because I know 4 squared is 16. And I know 2 squared is 4. So that means 2 squared squared is 16, which means that's 2 to the 4th. What's the 4th root of 16? 2. If you don't know that, you would have broken down your 16. And you would have gotten 4 and 4, 2 and 2, 2 and 2. This time we're looking for 4 of a kind. Oh, 1, 2, 3, 4. It's 2. Done. Okay? Don't waste your time. Work smarter, not harder. Okay, over here, again, I have the cubic root of 6 times the cubic root of 4 divided by the cubic root of 2. All of them are cubic roots. Hallelujah, praise the Lord. So, what is the cubic root of 3 times the cubic root of 4? Well, that would be the cubic root of 24 divided by the cubic root of 2, which is just the cubic root of 12. Well, 12 is not a perfect cube, okay? If I go and I try to simplify, though, I just get these numbers. I cannot make 3 of a kind. So what does that mean? That means this is already simplified. Okay. Cubic root of 120. 120 is not a perfect cube. So we're going to have to break this down. Factors of 120, you could go 12, 10. 2, 5, 2, 6, 2, 3. Now I've reached prime factorization. How many am I looking for? 3 of a kind. 1, 2, 3. That's 2. Cubic root of 3 times cubic root of 5 is cubic root of 15. Done. Okay. E, 16 to the 2/3 times 16 to the 5/3 divided by 2 to the 7/3. Well, lucky for us, in the numerator, our base is the same, so we can add those exponents. We can, add the exponents because they're being multiplied. So 16 to the 2/3 times 16 to the 5/3 is 16 to the 7/3, still being divided by 2 to the 7/3. What's cool about this, even though our bases are not the same, our exponents are. Think about what this would really be. This would really be the cubic root of 16 to the 7th power over the cubic root of 2 to the 7th power. So because the roots are the same, I can take the quotient of them, right? So that's really going to be 8 to the 7/3 power. Well, let's rewrite that as the cubic root of 8 to the 7th power. Think smarter, not harder. Cubic root of 8 is 2, so this is 2 to the 7th power, which I know is going to be a 128. I know that 2 to the 6th is 64, so times 2 again is going to be that 128. That's fun. All right, F, cubic root of 3 times cubic root of 18 divided by the 6th root of 2 times the 6th root of 2. Okay, so we're looking at this and we're thinking, well, this is nice. Our top two are the same, so technically I can multiply those two together. And our bottom two are the same, so technically I can multiply those two together. So we can do that. Excuse me. But actually, because our top and our bottom are not the same, I want to show you something first. Let's focus on that bottom. Our top, let's just leave it. Cubic root of 3 times cubic root of 18. Or if you want to multiply those numbers together, you can. If I were to rewrite the 6th root of 2, you should know that that is 2 to the 1/6 power. And then 2 to the 1/6 power. Well, those bases are the same, right? And so if I have the same base and I'm multiplying them, I can just add the exponents. Well, what is 1/6 plus 1/6? 1/6 plus 1/6 is 2/6, which is 1/3. Well, if this is just 2 to the 1/3 in my denominator, is that not the same thing as the cubic root of 2? And now all of them have the same root, which is phenomenal because now I can just say that this is the cubic root of 27. And in my brain, I'm just doing 18 divided by 2 is 18 divided by 2 is 9 times 3 is 27. And I know the cubic root of 27 is 3. Pretty awesome. Okay, I really like ones like G and H. This is fun for me. All right, we're taking the 4th root of all of that stuff. All of that stuff. Take it piece by piece. The 4th root of 32 is actually 2. The 4th root of x to the 6th. Think about that. The 4th root of x to the 6th. That's really x to the 6 over 4, which is really x to the 1 and 2/4, which is really just 1 1/2, right? So 1 comes out. 1x comes out. But how many are left underneath that radical? 2 of them. Right? Because it's still going to be the 4th root. So 2 of them. Maybe not simplify it. That might confuse you. We want to leave it as 2 over 4 because it's still going to be the 4th root. Okay. So if you can take the number of the root from the exponent, one whole thing comes out. Or maybe 2 whole things come out. Or maybe whatever. think about making your 4 of a kind here. If I have x times x times x times x times x times x, that's x to the 6th power. If I take the 4th root of that, I'm looking for 4 of a kind. 1, 2, 3, 4, that's x. What's left over? The 4th root of x times the 4th root of x. Well, what is that? That's x times the 4th root of x squared. That's what I want here. Okay, think of it that way. That's probably the easiest way. So one of them came out. 2 of them stay inside. Okay. What's the 4th root of y to the 5th? Y times y times y times y times y. I want 4 of a kind. There they are. What's left? That. The 4th root of z to the 12th power. How many groups of 4 can you make in 12? 3. That means there's nothing here for z. So that's ugly. I want to rewrite it. We had 2x, y, z cubed, 4th root of x squared, y. You want to make sure that 3 and that 4, that it doesn't look like a 34th root. I don't want it to look like z like that. Okay. Try to space it out a little bit. Yes, I know I'm being crazy. I'm tired. I waited to the last minute to make my video. It's 8:54. It's my bedtime. Not really, but close. Okay. H. We're doing the same thing. The cubic root of now 40, x to the 7th, y cubed, and z to the 5th. Cubic root of 40. Well, 40 is not a perfect cube. So I need to come over here and say, okay, what are factors of 40? Let's go 22. Let's go 2, 10. Let's go 2, 5. Boom, boom, boom. 3 of a kind. Boom, boom, boom. 2 cubic root of 5. Outside, inside. Outside, inside. Leave some space. Okay? Then I'm taking the cubic root of x to the 7th. How many groups of 3 can you make in 7? 2. With how many left over? 1. Cubic root of y to the 12th. How many groups of 3 can you make in 12? 4 of them. How many left over? None. Don't put the y there. Z to the 5th. How many groups of 3 can I make in 5? 1. With how many left over? 2. If you want to put the 1, fine. I really wouldn't though, because it's understood. Done. Final answer. Okay. In I, you cannot combine those because it's being added. And when I'm adding, these numbers have to be the same, okay? But lucky for us, didn't we just reduce the cubic root of 40? Yes, we did. And what did it simplify to? It simplified to 2 cubic root of 5. Holy Mother of God. We have the same exact thing. So now we can add them because they are like terms. Think of this as 2x plus 2x because I have the exact same thing here and here, which is what I want in order to add or subtract. So this is going to give me 4 cubic root of 5. Not 4 cubic root of 10, not 4 sixth root of 10, not 4 sixth root of 5. These are the same. Think of those like variables. You're just adding the numbers. Okay, but those radicals have to be the same in order for you to add or subtract. If you're multiplying or dividing, different story, which is like what we see in J. When I'm multiplying or dividing, the root has to be the same, but what's underneath that radicand does not. So therefore, in this case, I really have the 5th root of 7 divided by the 5th root of 8, which, yes, that is the 5th root of 7 over 8, but that's not simplifying it. There's got to be a way that we are simplifying this. So let me rewrite as fractional exponents just to see what I can work with. So this is 7 to the 1/5 power. Technically, that's 8 to the 1/5. But I'm just like stuck on this 8. And the reason why I'm stuck on this 8 is because I know that 8 is a perfect cube. 7 is not a perfect anything. 7 is a prime number. But 8 is a perfect cube, which means technically I could rewrite this as 7 to the 1/5 over 2 to the 1/5 times 2 to the 1/5 times 2 to the 1/5, because I know that 2 times 2 times 2 is 8. I have not changed my problem at all. What I've actually done is make my life a little bit easier. And I'll show you why. 7 to the 1/5 divided by 2 to the now 3/5. The problem with this whole entire problem is that I have a radical in my denominator and I can't leave it there. So I rationalize. Raising it to what power? What is going to make that a whole number? What can I add to 3 over 5 to make a whole number? 2 over 5. Which means now I have the 5th root, because they're both dividing by 5, of 7 to the first power, right, times 2 to the second power over 2. Well, that's just the 5th root of 28 over 2. Final answer. If I wouldn't have done this step, then I would have done, let me just come over here, 7 to the 1/5 divided by 8 to the 1/5, and then I would have said, okay, well, then we have to divide or multiply by 8 to the 4/5 and 8 to the 4/5. So then that gives us 8 in our denominator, and then the 5th root of 7 times 8 to the 4th power, which is going to be this big number that I then am going to have to break down, right? To then simplify. I'm taking more time. That's what they're saying of when you look at that radicand or whatever, you want to make sure it's simplified all the way. You wouldn't have been able to leave it as the 5th root of 7 times 8 to the 4th over 8. That's not simplified. Who wants to do 8 to the 4th multiplied by 7 and then take the 5th root of that? Nobody does. That's why you need to recognize those good numbers and rewrite when possible. All right, now we're doing K. The cubic root of 4 over 9x. So I'm going to rewrite this. This is now going to be the cubic root of 4 over the cubic root of 9x, which then I know 9 is another special number. Remember, 9 is 2 squared, or 9x. We could say that, oh, never mind, we can't say that that's 2x times 2x, because that would be 9x squared. So then we can just say, let's see. We can say that this is, hold on. Cubic root of 3 over. Let's do, sorry, my notes were, it was a different problem. So, hold on, let's come back to that. Let's do L real quick. Okay, L is going to be the 5th root of 3 over the 5th root of 4. But I know that 4 is really 2 times 2. So we can do that. Or we can just go the route of, working it as is, and that's fine. So really we know that this is 3 to the 1/5 over 4 to the 1/5, which means I'd have to multiply, oops, I don't know why I did an equal sign, which would mean I'd have to multiply by 4 to the 4/5. Okay, I'm showing you if you don't kind of work smart with your numbers. So then this would be the 5th root of 3 times 4 to the 4th over 4, which then simplifies to what's 4 to the 4th power? Well, that's 256, but then I'd have to multiply that by 3. So notice I'm already in a headache. 256 times 3. Ugh. Well, let me see. Let's do it this way. Times 3. 3 times 6, 18, 15, 16, 3, 5, 6. 668. My God. Now I have to break that down and take the fifth root. See, I'm done right there. My brain just says, no ma'am. But look what happens if I do this. If I say, well, this is really fifth root of 2 times 2, right? Which is really 3 to the 1/5 over 2 to the 2/5, which then I would just need to multiply by 2 to the 3/5. Then that would be the fifth root of 3 times 2 cubed over 2, which would then be the fifth root of 3 times 8, which I know is just 24 over 2. I want to double check real quick, but 24, 12, 2, 6, 2, 3, 2. Can I make 5 of a kind? No. So the fifth root of 24 is already simplified. So there is my answer. So much easier when you recognize those perfect squares, those perfect cubes, those perfect whatever. Because if not, you're going to get these big, huge numbers, and it's just going to be so hard to do. Remember, all of this is supposed to be done without a calculator, okay? All right. M, cubic root of x to the 10th, y to the 5th, divided by the cubic root of x squared, y. So what we can do is we can actually just say that we're taking the cubic root of this entire fraction, which means then we can do some subtraction. So now this is the cubic root of what's x to the 10th divided by x squared. That would be x to the 8th, but that's not what... Hold on. Yeah, x to the 8th. And then y to the 5th divided by y is just y to the 4th. And then I simplify this. Remember, I'm taking the cubic root of x to the 8th. How many groups of 3 are in 8? 2. So I'm taking out x squared. How many are left? 2. How many groups of 3 can I make in 4? 1. How many left? 1. So here's my final answer. 1 over 5 plus radical 3. We've done these before, so that means we're going to have to multiply by 5 minus radical 3 over 5 minus radical 3. 5 minus radical 3 over. When we multiply those conjugates together, we're going to get 25. Then you would get a plus 5 radical 3 and a negative 5 radical 3, so those cancel out. And then you're going to get a negative 3. Negative 3. So then that's just 5 minus radical 3 over 22. Same thing with O. You're going to multiply by radical 6 plus radical 2 over radical 6 plus radical 2. So radical 6 plus radical 2 over first times first would be radical 6 times radical 6 is 6. Outers would be plus radical 12, but then you get the minus radical 12, so those cancel out. And then last would be a minus 2, so then you get radical 6 plus radical 2 over 4. Okay, and then last one reminds me of Harry Potter. I don't know why. The platform, I guess, 9 2/3. Isn't that the platform? Maybe not. I don't know. 4 times 9 2/3 plus 8 times 9 2/3. Hey, guess what? That 9 2/3, that's the same root, same number underneath, everything. That means we can add these together. 12 times 9 to 2/3. Okay? And that is our final answer. We can actually leave it just like that, because even if I rewrite it, 9 squared is 81. I can't take the cubic root of 81. So this is simplified. So if you want to rewrite it, you're more than welcome to, even if you want to rewrite it as this. All of these are the same. They're all correct. Typically, we leave it our answer in the way that it was given to us. So if it was given to us with fractional exponents, we can leave it with fractional exponents. If it was given to us in radicals, we want to leave it in radicals. But I'm okay with all three of those answers as final answers because they are all simplified. Okay, I know this was a longer lesson. That's what I'm saying, that 6.0 is going to be really beneficial to you guys. So yeah, good luck. We'll chat soon. Bye.